a little bit about large format additive manufacturing. That phrase, or the acronym LFAM, is used at an increasing rate to describe different markets, different services, and different products. But what we have found is that it's kind of used ambiguously, right? You'll find that one machine that is described as large format may be very distinctly different from that of another machine which is considered large format. And so what is large format? How do we know what large format is, and how do potential users how do they distinguish between one large format system and another? There's not a perfect answer for that. What we have done is we've tried to put together a map of sorts. Will be helpful for folks like yourselves to, again, chart the large format additive manufacturing landscape. So the first step in doing this from the highest level is really to evaluate LFAM based on the additive manufacturing technology in consideration. So that said, a large format printer that is used in like an SLA-based printer or a DLP printer or even like a powder bed fusion printer, it's going to be drastically different than what we find in the material extrusion AM technique or in the DED technique. And since our focus and where a lot of the LFAM activity has taken place over the past couple of years is in material extrusion, we're going to focus a little bit more on the variables, if you will, that can help folks, again, kind of navigate that path there. And there are 5 different elements that we're going to focus in on to serve as borders, if you will, to serve as borders as you guys are mapping out that process and to try to bring some, to make some sense of what you're seeing out there. Some of these are very much printer centric, things that you can probably find from a spec sheet. Other things are more observed, or at least areas that should spur additional conversation with your potential buyers or your service bureaus if you're working to buy parts versus owning a machine. So those 5 things are build volume, which is the simplest thing, extrusion specifications, chamber control, about gantry systems versus robotic systems, since that's been a hot topic as of late. And then the last thing we're going to talk about is operation, or more specifically, the range of workflows that can be expected with different LFAM systems. So we'll start with build volume. And when we look at material extrusion specifically, there's a lot of different sub-techniques that are included, obviously, under that extrusion umbrella. The 2 most prominent are filament-based systems and pellet-fed systems. And so there are large format filament-based systems that have been marketed for a long time, some that are very well known and that have been put to good use. You typically see a large format filament system having a build volume that is larger than 4.5 cubic feet. And that's equivalent to about a 1.5 by 1.5 by 2 foot build volume. And there's obviously some that are a little bit bigger than that, but that's usually pushing a larger filament-based part. Where large format pellet started, so pellet-fed 3D printing or fused granulate fabrication in the 2014 timeframe, is much larger than that. So typically you see these systems that have a build volume of larger than 250 cubic feet. That's about a 5 foot by 5 foot by 10 foot build volume. And we all know, or if you don't know, there are systems out there that have travel distances that are much larger than that in the pellet-fed 3D printing space. So then there's this in-between area, right? And this is actually where we at JuggerBot play our Tradesman series. You may have, some of you may have heard us refer to it as a medium format industrial 3D printer, because our build volume and other ones in our class are stemming around the 48 cubic feet and higher volume, which is equivalent to 3 feet by 4 feet by 4 feet. So much larger than what you see with large format filament, but significantly less than what you have with some large format filament based systems. All larger, all large format, arguably build volumes, but when it comes to trying to draw a more apples to apples comparison, you really have to categorize the different printers based off of build volume here first and foremost. For clarity, I'll refer on these next couple of slides to large format, large pellet, and medium pellet, just so that again, there's some clarity in terms of what's important to note with each ones, and again, hopefully help comparing the different alternatives for all you folks out there that are looking to either buy or use. So build volume is tied directly into extruder specifications. And so when we talk about extruder, I should say, kind of complements each other, not directly goes with them, but complements definitely. So in extruder specifications, we're referring to three things in particular. The first is throughput, which is how much material can be extruded over a period of time. The bead width and the layer height, which are both referring to the cross-sectional bead width and then the layer height for a particular path that is being extruded. And so on the right-hand side here, the chart that we've provided gives you the averages and the comparison of averages between large filament, large pellet, and medium pellet systems. So max throughput, you can see basically in essence, the large filament printers, they're going to have the slowest throughput. They're going to have the finest bead or design freedom in the kinds of parts you're going to make. The large pellet systems, they're going to pump out the most amount of material. They're going to have the fattest bead, the biggest bead, more often than not. And then the medium pellet systems like ours, that's your middle of the road. That's kind of the balance of both things. It's very fast in terms of throughput as in comparison to filament-based systems, a smaller bead than what you find with large format pellet systems. So again, a balancing act of both things. And it's important to note some of this because bead geometry specifically, so defined by the bead width and the layer height, those are going to play a direct impact on how large a part one person or an operator can actually make off a given system. So there is a consideration for how large a part can be made how large a part can be off of layer time specifically. That's pertaining to the amount of time that can pass before, on the minimum side, the minimum amount of time that can pass before a second layer can begin or another layer can go on top of the prior layer that was just deposited, giving that prior layer enough time to cool adequately enough to maintain its own shape, or the maximum amount of time that can pass before the layer that was previously deposited is cooled too much and have issues with layer adhesion. So if you're printing in a vacuum, same material, there's no external factors that are affecting the print, the thermal mass or the ability for a printed part to retain its heat, right, giving it a longer lead time, making a bigger part, is always going to lean towards larger pellet, right? While the smaller bead is going to have less thermal mass, a shorter layer time, and it's going to have trouble building larger parts. Now, it's important to note that there's a balancing act here too, right? Your minimum lead time is typically a driver for to print a part, whereas your maximum layer time is more often than not going to be the true deciding factor on how large of a part you can make, not necessarily your build volume. And so it's just important to note this because you'll see that, especially when it comes to some high temperature, there are larger printers that, based off of the extruder specs, are capable of printing really large parts, sometimes with higher temperature materials, whereas you're not going to have that same kind of success with maybe some of your medium format or your filament-based printers that are equipped in the same way. That kind of leads me into my next category, which is chamber construction. And this is where it goes hand in hand with bead geometry and thermal mass of a given bead. Especially when you want to print high temperature materials, printing large parts is very difficult for those smaller beads. That's why you typically see large format filament systems that are the more industrial grade. You have better better reputations for repeatability and reliability. Again, especially with high temperature materials, their build chambers are usually built in a way that allows them to get above 200 degrees Celsius. Step back, actually, there's three different common types of chamber construction that you find in the material extrusion world. The very first one is an open air chamber, in which case, there really is not an enclosure. It's just the printer itself. It's subject to external variances that could be stemming from somebody opening a garage door during the middle of a print or somebody walking past the printer at any given time. That could be the air conditioning kicking on, or that could even be a difference between printing in one part of the world versus the other. The next type of chamber that's common is just an enclosure, right? So this is where essentially it could be a polycarbonate barrier. It could be made out of metal or other plastic. It's just basically protecting the chamber, the printing environment from those external factors that may be causing any kind of variance. But the third option is environmentally controlled chambers, and this is different than enclosures in the fact that it's constructed in a way where the operator can actually manipulate what's happening in the process by removing humidity or mitigating humidity and increasing the temperature of the build chamber specifically. So is kind of complementary to the thermal mass of larger beads. You'll find again that the smaller beads require higher temperatures. They really require environmentally controlled chambers in order to be able to create larger parts with consistency. Again, especially as you start to climb the ladder, the polymer pyramid, more specifically for higher temperature materials. That's also why you can see some larger format systems on the pellet side that can print much larger pieces because they have the thermal mass from the extruders that allow them to really control how fast or how slow the parts are cooling down and manipulate layer time based off of that thermal mass. And that's also why in the medium format space we have a balance of both things. We don't need necessarily to get up to 200 degrees Celsius or higher in the chamber. Leveraging the larger bead and the increased throughput of the extruder in order to be able to consistently and repeatedly print large parts with high temperature materials, and that's above 80 degrees Celsius in general. All right, so moving into the discussion between gantry systems and robotic arms. Again, this has been a hot topic as of late specifically, and in a discussion that quite frankly transcends 3D printing altogether. This is something that I'm sure as many of you probably have researched is an ongoing discussion in the CMM world, in if you're looking at pick and place machines or routers or mills, there's people that are on the robotic arm side of this and people that are on the gantry side. And I think that there's a lot of acceptance now between which systems do better or where each one maybe thrives. There are obviously some things about 3D printing that are specific that we've seen, and we are admittedly biased because we're building systems with gantry-based extruders. I'm sorry, gantry-based systems. Typically, I think it's accepted that if you leverage those first three things that we just talked about, the build volume, the extruder specs, and the chamber construction, those will help to have a more comparable view at gantry or robotic systems. But there's definitely, it seems like there's at least a purpose for each version. And so some of the, I think, more generally accepted advantages of a gantry system would definitely be, because of the construction of a gantry system, faster travel speeds and more accuracy in the printing process. And then the last thing for a typical advantage on our gantry system is the ease of operation. Whereas for robotic arms, given that they are out there, there's more and more being installed. The typical advantages really refer to the type of parts and geometries that can be made. Now, there's still limitations with bead geometry, but especially if you're looking at parts that require like 5-axis printing, a lot more unique designs can be accomplished using a robotic system. And then because of that, because you can print in multiple axes, you have potentially at least more control over the isotropic properties of whatever part that you're trying to print versus especially a 3-axis gantry system.